was having some screen tearing issues, but I think we're good now. So let me pull that a little bit closer. All right. Welcome to this unofficial part 2 of this object detection series. So what we're going to try to understand in this video is how to evaluate a bounding box prediction. So, we have some target bounding box for an object, and we have some predicted bounding box, and we want to have a way of quantifying or measure how good is our predicted bounding box for that object. And for that, we're going to learn about a metric called intersection over union. And then we're also going to implement that in PyTorch. So that'll be fun. So without further ado, let's get started. Let's roll that intro, and then let's get started with intersection over union. So the question is, how do we measure how good a bounding box is? So we have an image with, in this case, a car in it, and we are given a target bounding box for that object. And then we have some prediction bounding box for the same object. And I guess here we can kind of visually inspect and see that, well, I mean, it's not a perfect bounding box, but it's not terrible either. So I guess this bounding box is sort of okay, but we can't be, visually inspecting every bounding box prediction. And also, we want to have a way of quantifying and saying sort of more specifically how good this bounding box is. So what we're going to do is we're first going to calculate intersection of those two bounding boxes, which is this beautifully drawn yellow figure. And then we're going to calculate the union, which is the combined area of both of those bounding boxes, which is this, again, just beautifully drawn pink region. So the metric we're going to use is intersection over union, and it's pretty self-explanatory in a way. The IOU is equal to the intersection, which is the yellow area. And then we divide that by the union, which is the area of the pink region. And so, I guess more formally, it's the area of the intersection divided by the area of the union. So what we're going to get from this is a value between 0 and 1, indicating how good the bounding box prediction is. So, for example, if we have a bounding box, if you have an IOU score of 1, then that means that the prediction box was, absolutely perfect. And if we have a IOU of 0, then that means that there were no intersection between those two bounding boxes. And sort of as a rule of thumb is that if your IOU is greater than 0.5, then it's considered decent. And this is sort of the mark where you go from saying that a bounding box is actually accurate if it has an IOU of 0.5. If it's greater than 0.7, you say it's a pretty good bounding box. And if it's greater than 0.9, then that bounding box is almost perfect, because you're almost never going to get, or you are never pretty much going to get a IOU of 1. But still, the question or the solution of how to find this is still not very clear. How do we even get the intersection? Because remember that all you're given is just two lists of numbers. One list for the first box and then for the second box. And from these 4 values in the bounding box, we can form the bounding boxes for those two. But we can visually see what the intersection is, but it's not very clear exactly how we do it from just the numbers. So just one thing to keep in mind here when we're doing all of these calculations that we're going to do or to show for this example is that the origin in computer vision for images is in the top left corner. So we have that the origin is at the top left, and then as you go to the right of the image, as you move horizontally, your X value is going to increase, and then as you go down vertically, you're going to increase the Y value. So for our image here, the origin is 0, 0 at the top left, and then at the bottom right, depending sort of how large your image is, maybe it's 300 by 550 in this case, because it is slightly taller than it is wide. Or, yeah, I mean, it's quite a lot taller than it is wide. But anyways, so for our image then, what those values, as I mentioned in the previous video, what these values correspond to are the corner points for those bounding boxes. So now what we are looking for is the corner points of the intersection between those two, which in this case would be the yellow region. And as we can see from this example, is that would be the red box top left corner point, and then the blue's bottom right corner point. But how we can find these more generally with a formula is that x1 rather for the top left corner point of the yellow box is the maximum of the x1 values of the two boxes. And in this case, since the red corner point of the top left is further to the right than the blue one, then we can see that the red one is going to be the maximum of those. And also y1 we calculate by taking the maximum of the y1 values of the top left corner points. So again, we can see that this is also the red point because it is further down than the blue top left corner point. So and again, this is also what we see, right? The top left of the yellow region is exactly the red point. For the bottom right corner point of the yellow region, we instead take the minimum of the x2 values. So the minimum in this case is going to be the one that is most to the left of the bottom right corner points. And in this case, that's going to be the blue point. And then for the y2 value, we're also going to take the minimum of the y2 values. And again, since the blue one is higher up than the red one is further down than the blue one, and we want to take the minimum, so again, we're going to get the blue one for that, which is exactly what we expect. So let's look at a little bit of a more difficult example to again illustrate this same concept. So here we have two bounding boxes again. We have a blue bounding box and a red bounding box. And our goal here is to find the intersection, or rather our goal is to find the corner point of the yellow region. Looking at the top left corner point of the yellow region, we first want to calculate the x1 value. And again, the x1 value is the maximum of the blue box top left x value and the red one top left corner x value. So the x1 of the two boxes. And in this case, that's just going to be, that's going to be the red one, right? Because it's further to the right than the blue one. So that's going to be the red one. And then for the y1 value, we're again going to take the maximum, but now the blue one is further down than the red one. So we're going to take the y1 value from the blue box. So moving on to the bottom right corner point of the yellow region, that's going to first be the minimum of those two boxes, and the minimum of those two is in this case going to be the blue one. So now we have x2 from the blue box, and the y2 is going to be the minimum of those y2 values. In this case, that's going to be the red one because it's further up than the blue bottom right corner. So again, we see that this formula holds in general. So the formula for calculating this yellow region, the corner point, is that we take the maximum both for x1 and y1, and we then take the minimum of x2 and y2. All right, so that's for finding the corner point of the intersection box. We then need to calculate the areas, and then we also need to calculate the union. But I think I'm going to show that in the code because now we've done all of the tricky part. So if you follow this far, I think it's going to be relatively easy following the code as well. All right, so what I've done is that first of all, we have some test cases that I've done, unit tests, so that we can make sure that our implementation is actually correct. I'm not going to go through that in this video, the test cases I did, but it's going to be on GitHub if you're just, I guess, curious to see how that looks like. But anyways, we're going to go into this iou.py file, and our goal now is to do this implementation. So I guess what we need is import torch. Then we're going to do define intersection over union. And we're going to get some boxes, boxes predictions. So I'm going to call it boxes preds. I'm also going to get some boxes with their labels. So boxes labels. And so you can imagine that this is just one box with 4 values and one box with 4 values for the label. But this can actually be a batch. So I'm going to do it in a general implementation so that you can send in an arbitrary number of examples and it's still going to work. So what we want to do, I guess, first of all, is just get box1 x1. So that's going to be boxes preds of ... 0 and 1. And then box1 y1 is going to be boxes preds ... 1 and 2. And so if you're unsure about this ... that just means all the dimensions previously. You know, I guess this is not really needed, although you'll see later on it's actually useful to do this when we're implementing the YOLO algorithm. But, you know, for now you can just say that it's n comma 4, where n is the number of bounding boxes. All right, so that's the dimensions of a bound boxes preds. So we can maybe write that boxes preds shape, and then boxes labels shape is n comma 4 as well. And then so we need box 1 x2 is boxes preds 2 and 3, and I guess we don't have to do this. We can just copy it like that, and then we're going to need y2, and then we're going to need box 2 x1, box 2 y1, and then let's see what we need. We need to copy those, and then we need x2 y2. All right, so for, let's see here, box, that's going to be 3 and 4, and yeah, so damn, this explanation was not that good. So basically what I'm doing here, why I'm doing this 3 to 4, is because I want to slice the tensor to maintain its shape. So I want the output tensor shape of this to be n comma 1. All right, if you would just index with this, like doing 3, that's going to remove the second dimension of the tensor just to be n. But I want to keep it as n comma 1. So that's why I'm doing this slicing in this way. And then we're just going to do pretty much the exact same thing for box 2, like that, 3 and 4. So, you know, here I'm not doing anything in particular, really. I'm just extracting the points. And then we want to get x1, and this is the x1 for the intersection. This is going to be the maximum of box 1 x1 and box 2 x1. Then and let's copy that so we don't have to copy that. And we're going to do that for y1. We're going to do that for x2, and then we're going to do that for y2. So for y1, we're going to take box 1 y1, and then box 2 y1. Then for x2, we're going to take the minimum, and we're going to do that also for y2. And that's going to be box 1 x2, box 2 x2, and then box 1 y2, box 2 y2. All right, so now we have the corner points of that intersection. We're going to do intersection is the x2 minus x1, right? That's the width of the bounding box. Then we're going to do times y2 minus y1. Now there's one edge case that I didn't talk about, and probably I should have, is what if they don't intersect at all? So that's a scenario that we need to cover. And if you, I encourage you to just draw out 2 examples, 2 bounding boxes where they don't intersect. But what we're going to do is we're going to do clamp of 0. So we're going to do this subtraction, and if they don't intersect, then at least one of these are going to be 0. So again, I encourage you to draw this out just to get some better intuition. But this clamp right here, clamp, let's see, dot clamp of 0 is for edge k is for the case when they do not intersect. Because then if they do not intersect, then the intersection should be 0. All right. So then we need to do box 1 area is box 1 x2. So again, we've calculated intersection of the area of the intersection, but we need to now calculate the union. So we're going to calculate box 1 area and box 2 area. And that's just going to be box 1 x2, box 1 x1. Then we're going to do times box 1 y1 minus box 1 y2. All right. And I guess maybe just to be certain, because the area can't be negative, that it shouldn't occur, but maybe we can just do an absolute value just to be certain of that. All right. So we can copy that, and we're going to now calculate box 2 area, and it's going to be pretty much the exact same thing. We're just going to change that to box 2, box 2, box 2. All right. So now what we want to do is we want to return the intersection divided by the union, and the union is going to be box 1 area plus box 2 area. But one problem here is that we've added the intersection of those two areas 2 times, right? Once for the box 1 area and then once for the box 2 area. So this follows a more general formula. So that's the box 1 area plus the box 2 area minus the intersection. All right, that's just a formula for union. And then we want to add just 1e minus 6 just for numerical stability. All right, so that should be intersection over union. So now let's try and run this IOU test. Oh, god damn. Oh, yeah. So one thing, okay. So we can do a box format as well. Since, you can have varying of these box formats. I told you can either have the corner points, or you can have one corner point and you can have the height and the width. But there are also scenarios where you have the midpoint. So you get 2 values corresponding to the midpoint of the bounding box, and then you get the height and the width. And that's actually what you get for the data set for the YOLO, which was based for the YOLO algorithm. So that's perhaps important to cover as well. So I'm going to do box format is midpoint, we can set that as default. But so this right here, this is if box format is equal to corners. I'm just going to call it that. That's what I mean when I say that we have the top left and the bottom right corners. But if we would have, if box format is equal to the midpoint, then we need to translate this into the corners. So in this scenario, we don't have to do anything. But if it's the midpoint, we need to do some calculations so that we make sure that it's at the midpoint. So that we make sure that we have the top left corner and the bottom right corner for the bounding boxes. So actually, I'm just going to copy those in, and I'll explain them. So they aren't really too difficult, I think. So all right, so basically, if we want the x1 of the first box, then this is the midpoint. So if we divide the width of that box by 2, then we'll get the top left x1 coordinate. And then for the y1, again, we're subtracting the height by half, because we're at the center of the object, and then we want to get to the top left and the bottom right coordinates. So we're just subtracting or adding the height and the width by half. So basically, if the box format is midpoint, which we're going to use for the YOLO algorithm, then we'll just convert them back to the top left and the bottom right corner. Else, if the box format is corners, then we don't want to do anything, right? So then it's already done. All right, so let's go back to our test case, and hopefully it works now. Failure is 2. All right.
2 hours later.
Oh my god, that took so long to find. Jesus Christ. There should be boxes, labels. I'm so tired. Boxes, labels, labels, labels. I'm not even sure how it got some of those test cases incorrect, to be honest. That makes no sense. Oh yeah, that's because most of my tests are for the midpoint. But yeah, that makes sense. All right, but it did fail. So now we ran it and we got all of them correct. All right, that's pretty nice. So yeah, hopefully, well, let's do some doc strings as well for this. All right, so now we got doc string and so yeah, we take as input these boxes pred, boxes labels, box format, and then we output the intersection of a union for all of those examples. You know, one thing I just realized is that this implementation is, we don't even, I think this is, well, we use Torch here, so it's dependent on Torch, but with very, very minimal changes, you could use this for NumPy or I guess TensorFlow as well. So this was intersection of a union. Hopefully you were able to follow, even though it's a very pretty simple concept. It can be pretty complicated sometimes. All right, so thank you for watching this video, and I hope to see you in the next one.